we're having a little discussion here about this question here. It was on the daily task on, I believe, April 14th or so. And it's under the Coulombs Law, uh, sort of little info sheet, a couple of practice questions here. Here it says 3-point charges are positioned as shown. Determine the net force on A. All right, so A is this one. 5 coulombs, 3 and 2. These guys are negative. And it appears there's 2 meters distance between everything. Okay, and this looks to be like, then, I guess, if it is 2 meters, 2 meters, and 2 meters, it would end up being an equilateral triangle here. So 2 meters, 2 meters, and 2 meters. So if we want to figure out on A here, the force on A, we realize that that's 5 and that's 2. So it's going to be pulled up, this one. But then this is positive and that's negative. Sorry, I wanted to mention that. Positive, negative. So it's going to be pulled up. These are both negative, so this guy's going to push it down. Okay, so if we go to the solution, which is solution 3 here, let me go ahead and move this down a little bit. Calculate the values of the forces. What they've done here is they've kind of called this force 2/3 and force 2/5, meaning, and I guess the 5 represents this 5 coulomb, and the 3 represents this 3 coulomb, and then the 2's represent this 2 coulomb. So essentially, then you're going to use Coulombs Law. So force 2/3 is K Q R squared. All right, so here it is. So it's going to be this much. All right, so 9 times 10 to the 9 times 2 times 3 times 2 squared. Okay, and then this is going to be in the direction shown. And so that's force 2, 3. So that's this one. So it's going to be pointed down this way, down that way. All right. And then force 2, 5 is calculated at 2.25 times 10 to the 10. Same calculations, but with a 5 here rather than a 3. All right. And this is also now in the direction as shown. Right. And so now, basically, what's going to be happening here is they're going to add these forces, okay? So here you've got a force pulling up and a force pulling down. And so they've chosen to use vector addition. So that's this force pulling up, and then afterwards they're going to have a force pulling down. For the sum of two forces, it's this plus this gives that right there. Okay, and using a little bit of trigonometry, you can determine that this is a 60-degree angle. Okay, now, because you know this side length and that side length, I'm guessing they're going to be using the law of cosines maybe here. It appears, yes. So they're going to be using the law of cosines, which is this leg and this leg each squared and summed. So it's the square plus another square minus 2 times the two forces times the cosine of the angle between them. That's what, so this is the law of cosines right here. All right. And you notice that this is force F25, and this is F23. Here's F23 again, and F25 again, and here's the angle between them, and then notice it's squared. So the net force is the square here. And so, you know, I probably would have used our technique that we learned in class, which is called the component method. This is the geometric method, so, you know, either way, it doesn't matter so much how you do it. This is now your net force. They square rooted it, it looks like, too, because notice the square is gone in this example. So I'm assuming that they square rooted that. Now, in order to get the direction, you're going to have to use the sine law, right? Using the law, it's not written, law of cosines. That's why. There we go. So I'm going to save that. Okay. Now, we're going to use the sine law. The sine law works like this. So basically what do we want to do is we want to figure out this angle here so that we can determine what angle this dotted line, this dotted vector line is going. So in order to figure out that angle, you need its opposite side, right? And then, so basically they're going to call that angle A. So sine of A divided by its opposite side, which is force 23 here, should equal the sine of 60, which is this angle, divided by its opposite side. And that's the answer that we got from the previous cosine law. So you can kind of see that this side is this, okay? And now, after you do a little bit of algebra here, you're going to, simplify this, and you're going to go ahead and get 37 degrees. This is the law of sines. And so therefore the net force is given as, 1.96. Well, they rounded it to 2 for their final answer. And it's at 37 degrees from the line joining the 2 and 5. So it's basically this. It's 37 degrees from that line there. Okay. And that's how they solved that one. Now, let's look at solution number 4 here. Let's go back up and look at question 4. So the charge on 2 pith balls are like little styrofoam balls that can be charged, and they're really lightweight. So therefore, their mass doesn't really have an impact on what's going on, or a little very small impact. So you can start measuring charges and things like that. Anyway, the charge on 2 pith balls can be calculated by knowing their masses and observing the angle of separation between the 2 balls. If the 2 balls are equally charged and they are suspended by strings that are 1 meter long, calculate the charge on the 2 balls. And so here it is. We've got 3 grams, this one and that one each, and they're charged for whatever, some kind of charge. We don't know what it is. And after they're sort of laid in this position, they repel each other because they must both be positively charged or must both be negatively charged because they're repelling. So because they're repelling, you've got some sort of outward force here, okay? But they can't repel like forever because at some point the gravity on these things will kind of keep it in the strings, the tension in the strings here as well. So let's go ahead and take a look at the solution for this one. Solution 4. So here, this blue diagram, the force between the 2 pith balls can be calculated by knowing their masses, observing the angle. Using the following information, calculate the electrostatic force. Here's the solution, okay? So basically, you've got a force of gravity here. You've got an electric force pulling out, and then you've got a force of tension here, okay? This force of tension, though, it's balanced. So basically, this force of tension has, I'm going to zoom in on this diagram here. Zoom. Oh, shoot. Let's zoom in. So this force of tension here has a component that goes that direction and has a component that goes up as well, okay? Now, the component that goes in this direction should be equal to the electric force, and the component that goes up should be equal to the gravitational force, because this is sort of, you can kind of assume that this thing isn't moving now. It's sort of just sitting there, okay? So if that's the case, its left and right forces are balanced, and its up-down forces are balanced. So basically, what you can say is that the force of tension in the y direction is equal to gravity, and the force of tension in the x direction is equal to the force electric. And the force electric is due to the fact that these 2 balls here have a charge. All right, so solve, or using the components to solve. So vertically it's balanced. So therefore the force of tension, cosine of 15, is equal to the force of gravity. Here we go. So this is 15 degrees because you split it in half. And so if you kind of take this as a triangle, then the force of tension, cosine 15, so this is the vertical, the the vertical component of this, right? So you can kind of think about, think about that. Can I get a line here? Here we go. So basically, I've got like a line that comes down like this. That's my vertical component, and it should have it's adjacent to this angle 15 right here. It's adjacent to this angle 15, and so therefore they're using the cosine. So that's your vertical component, right? I could even move this here so you can kind of see it a little better. This is the vertical component of the tension force. This angle is 15. And so there it is. Vertical component is that, well, that's equal to the force of gravity. Well, the force of gravity is 3 grams times 9.8. And so therefore the force of tension can be determined. Okay. But then horizontally, it's also balanced. And so therefore the force of tension sine of 15, the reason why it's sine of 15 is because if you take a look at this little thing here, oh, I can't click on that. Oh, yeah, I can. There you go. If we take this and we put it vertically or sort of horizontally instead, this component, this is the x component of this force of tension, right? Let me copy this. Oh, no, that's not what I wanted to do. Anyway, forget that. So I've got a vertical component and a horizontal component. The horizontal component is equal to Fe, so that's the horizontal component. Notice it's opposite of the 15-degree angle. And so why are they using opposite? Or why, because it's opposite, they're using the sine. Remember, SOHCAHTOA, sine is opposite. And so therefore, the force of tension sine 15 should equal the electric force. The electric force is that formula given back in the beginning of this section. So, well, they figured out the force of tension above. There it is. So, bang, they went ahead and decided to take the force of tension and put it there. They left this as a sine of 15. I'm probably going to plug that into the calculator. This is all of this stuff. And bang, we got that. R is the distance between these two, the two balls there. Oh, we're going to have to figure that out. Oh, looks like they're going to use the law of cosines here. Oh, what happened? There we go. Sorry. They're going to have to use the law of cosines again. Let me zoom out. That's what I was trying to do. Q and Q are equal, all right? And R can be calculated using the law of, so because that's 30 degrees. That's 1 meter, 1 meter. And so 1 meter squared plus 1 meter squared equals 2 times 1 times 1 times the cosine of 30. So this is about 52 centimeters here. So you substitute in those values here. Remember that your Q's are equal, so they just turn it into Q times Q, which is Q squared. And now you do a little bit of algebra, and it turns out that the charge on each ball is 4.8 times 10 to the negative 7. Okay? And there you have it, solution 4 there.